Hi everyone, in this video I'd like to show how to use an FTDI MPSSE cable. It's a neat little cable that FTDI sells. As you probably know, it can be used as a USB UART adapter. But the neat thing about this cable is it can also do SPI, I2C, and JTAG. So in this video I'm going to show how to use it for SPI. And so when you buy the cable, you just get this one cable, not the hub, but just the cable. And I have here a breakout board that I made a couple years ago that has a 3-axis gyroscope on it. And I will show you a simple demo program that configures it and then reads the X, Y, and Z velocities. So a quick little demo. When you start the program, it will show you details about every FTDI plugged in, and I only have one plugged in. And so you can tell it which one to use, which will be, alright, come on, focus, there we go, which will be 0. And then it will configure the gyroscope and start displaying readings for X, Y, and Z. So if I take this gyroscope, try to get it all in frame. Alright, so if I rotate, you can see that it's mainly the Z-axis for that rotation. There's your X-axis. And there's your Y-axis. And it's a 16-bit gyroscope, so that's why there's such sensitivity. Anyway, so it's a very simple demo program, and I'll show you how I made it. It's really easy, and let's get right to it. So the first thing we want to do is find that cable. So if you search for FTDI MPSSE, there's a listing for the cable right here. So they offer a few different versions. This first one is the one that I have. And so basically it has, half meter long wires, 3.3 volt logic, and then for SPI you can do up to 30 megabits per second. I believe the UART is up to 3 megabaud, and I believe I2C is obviously much lower than that, and I haven't looked into JTAG. But anyway, it's a really neat cable, and there's quite a few vendors that carry it. So you can buy it from DigiKey or Mouser. It's about $26, so it's a pretty good value. Anyway, so when you first plug it into your computer, Windows will automatically install the VCP driver, and that driver will let you use it as a UART. If you want to use it for SPI, I2C, or JTAG, you have to install the D2XX driver. So if you go down here, you want to click here, and go to Windows, and there's a executable right here. So click on that, install it, and you'll be good to go. And so after you do that, go ahead and open up Visual Studio. While that is loading, I'll point out a few other documents that'll be really helpful. So there's the data sheet. We'll open that up in a new tab. And the data sheet's nice because, well, first of all, there's a schematic, which is really useful. And it'll tell you what wire goes to what actual pin on the device. It also, actually I went past it. It'll tell you over here what color wire is used for what feature, and so we're using it for SPI, and it'll tell you that the orange wire is for clock, yellow wire is for data out, green for data in, and brown is the default for chip select. There's also 4 additional wires that can be used for chip select, so you can have a total of 5 chip select lines. So that's mainly what you use the datasheet for. It'll tell you what wires do what, and then it has the schematic. There's also the MPSSE library. We're going to do SPI. You'll want to download the demo code. Keep that open. And then also there is the documentation here. I'll open that up in a new tab. And I believe there was one more. Yeah, here we go. So back on the web page for the cable, there is an application note right here. So the application note will walk you through kind of a hello world type project, and actually no, I'm sorry, this is the usage guide for the library. The here it is. This is the hello world application note where they wire it up with a I/O expander, and they give you a couple pages of code. And one of the things I found is they do it kind of the hard way. Like, they create a whole bunch of function pointers to interact with the DLL, which you don't really need to do if you're going to use Visual Studio. Yeah, so you got all these function pointers. But it's a nice reference, and it's only about 16 pages. So there's the data sheet, there's the Hello World application note, number 188. And then this is the MPSSE SPI user guide, and it will document all the functions that we'll be using. So it'll tell you, the prototype and what it's expecting, what it'll return. So pretty simple, pretty straightforward. You'll probably want to download or bookmark those files. Anyway, so we'll go back to Visual Studio. Let's go ahead and create a new project. And we'll go to Visual C++. We'll do a console application. Let's give it a name. Go to OK. Don't click Finish. Go to Next. Uncheck precompiled header. You don't want that. I mean, you can leave it in if you want, but you really don't need it. And then go to Finish. Alright, so for some reason Visual Studio likes to include a bunch of stuff that you don't really need for a minimal program. I'm going to go ahead and delete them. So I'm going to delete these two headers. So you right click, you go to remove, and then you go to delete. Same with the CPP. Alright, so now we're down to one file, which is the way it should be. And let's, just to make sure we didn't screw anything up, let's make a really, really quick program. Okay, so this is a really simple, stupid program of Hello World. Just want to make sure nothing's broken. And there we go. So it says hi, it's waiting for a key press, and then it'll go away. Good. Okay, so nothing's broken. Now what we need to do is the SPI zip file that I pointed out has the library and some demo code. And so I'll walk you through it again. So you go into the main folder, go into Release, go into Samples, SPI. So there's a bunch of useful files in here. We need that header, FTD2xx.h. We need the LibMPSSE.lib, wintypes.h, and LibMPSSE_SPI.h. So we need those four files and only those four files. Go ahead and copy them. and you want to paste it into your Visual Studio project. So by default, that'll be under Documents, and you go to Visual Studio and Projects, and your project will be in here. But I configured Visual Studio to put it in my Google Drive, so I have it here. And so you go into the folder for your project, and you go into the folder that also has your project name, and this is where all your code is. You can paste it in here. Alright, so now we have those important files. We need to tell Visual Studio that they exist, because it doesn't know. So right-click on Header Files, Add Existing Item, and we'll add the header files. And repeat. And repeat. Alright, so we've added the 3 header files. We need to add the .lib file. Okay, so now Visual Studio knows that the files exist. One thing you need to change is open up wintypes.h, and you'll see an error right here. You just need to get rid of the sys part. So just pound include time.h. Alright, and just to make sure nothing is screwed up, we'll go ahead and run it again. Good. Okay, so now we can actually write the program. And it'd be a good idea to just add some comments as far as what wire is doing what. Alright, so that's just notes for future reference. We'll need to include some other files. We need to include windows.h. And we need to include the LibMPSSE SPI header. Alright, and then when we're actually writing the code to talk to the FTDI library, it will always return a status code, and we need to check to verify that there was no error. And so a very common thing we need to do is, if there was an error, we need to print it out and exit the program. So I'm going to go ahead and create a little helper function to do that. Alright, so this code will take a string, it will then print it out, and a new line character. It will then wait for the user to type any key, or press any key basically, and then it will quit the program immediately after they typed in a key, or typed in a letter. So now we can actually get to the important part. Alright, so before you can use the library, you have to initialize it. And you should really clean up after it right before you exit. There's a few variables we need to create. So it will always, or the functions will always return a status code, which is an unsigned long, but you need to create that. And then whenever, well, let me start over. For each FTDI device you have, it could have one or more channels. So this cable only has one, which means it can only talk to, or you can only have, you know, an SPI or an I2C or a JTAG, one of those at a time. You can't do multiple. And for each channel, you need to get information on it, and it will return a struct with that information. And then finally, you need a handle, which is just a number that refers to a channel. So we need to figure out how many MPSSE channels are available. Okay, so we have a 32-bit unsigned integer, which will store the number of available channels. We use the API to figure out how many channels are available by giving it a pointer to that number. It will return a status, and it should be 0, which is FTOK. If it isn't, then we had an error of some type, and you might want to print out a message and quit. So I'm going to print out error while checking the number of MPSSE channels. Another possible error is that it was able to execute this function, but for some reason there are no channels. So like if you forgot to plug in your cable, there would be a channel count of 0, and you'll want to print out a message for that. Otherwise, you want to print out a message saying how many there are. And let's verify this works. So that closed really quick. Not sure if you saw, but it said there was one channel available. Now we need to print out the details for every channel. So for each of the available channels, which again I only have one on this computer, it will go through this loop. We get the channel information by giving it a pointer to a struct called channel info and the channel number that we want to get information on. It will return a status, which should be FTOK. If it isn't, we want to print out an error. And if we didn't get an error, we want to print out details for that channel. So we print out the channel number, which is going to be I, so we're looping through it. The description, which is a member of that struct, and the serial number, which is also a member of that struct. There are other members. So there is description, flags, handle, ID, location ID, serial number, and type. And all that is documented in this file, the user guide for LibMPSSE SPI. It's also in the header file, which is right here, and it will tell you about all this stuff. So you got all your function prototypes, tells you kind of how the bits are all used for each setting. Anyway, we don't need that. And then we ask the user to type in what channel number they want to use. So print out a string, what channel number do you want to use, and then get that from the command line. Oh. Yeah, oops. Okay, scanf, not scanf. So if we run it again, so I only have one MPSSE channel available. It's channel number 0. There's the description, which is the model number for this particular cable, and the serial number. And so it'll ask what channel number to use. You type in 0, and now it's just going to exit. So we're back here. All right. We now need to open the channel and configure it. So when you open the channel, all it does is give you the handle. It does not actually configure the channel. And to configure the channel, you need to use the init function. Alright, the config options element is a number, and it's a bit field, and there's a few flags. The SPI mode, which could be technically 0, 1, 2, or 3, although I believe only modes 0 and 2 work correctly, at least according to the documentation. And then you need to tell it which pin you're using for chip select, which is going to be dbus 3. I'll cover that in a second. And we also want to tell it that chip select is active low, which is usually how it would be for SPI. Okay, so how did I know that it's dbus 3 for the chip select line? Well, we're using the brown wire, which was arbitrarily picked, but that's what we're using. And if we go back to the data sheet, so these are all the wires that are broken out. And we're using the brown wire for chip select, which is going to be pin 4. And if we follow it back, pin 5, yeah, that doesn't even line up very well. You can kind of see if you just follow them here. But brown is pin 5, apparently. If you follow it back, you'll see it's AD bus 3. So in the library they omit the A, it's just dbus 3. And so dbus 4 would be gray, dbus 5 is purple, 6 is white, 7 is blue. So that's how you figure out what name corresponds to what wire. There is another option for latency. And so it's a 8-bit number, unsigned, so between 0 and 255. A small number will make it work a lot faster, and a big number will make it a lot slower. It's kind of a balance between what you need and how much you're willing to slow down the PC with all the overhead. So we have this block of code that initializes the channel. The structure for ChannelConfig has a bunch of elements. Clock rate is going to be the clock rate in hertz. So I'm using 1 megahertz for this demo. Config options will let you set the SPI mode, the chip select pin that you're using, and chip select polarity, as I already covered. I already covered latency timer. So you call init channel, give it the handle, and give it a pointer to your ChannelConfig struct. And as usual, you check status, and if it isn't FTOK, you have a problem. And so the rest of this is really specific to my SPI device, which happens to be a gyro. And what we need to do now for this particular device, not necessarily for yours, is I need to write to a few registers to configure it, and then I'm going to enter into an infinite loop that will read from the X, Y, and Z registers and print them out. Alright, so this block of code just writes to the SPI device. I'm sending 6 bytes, and again these are specific to my particular SPI gyro. The first byte that it expects is the register number, and then bit 6 will be high for auto increment mode, and bit 7 will be high for read mode or low for write mode. And then you just give it the values, so the register, or the value for register 20, 21, 22, 23, and 24. And when you do an SPI write, it will also tell you how many bytes or bits it transferred, and you give it a pointer to a number, and that's where it'll put it. And you need to give it a configuration number or bit field, and you tell it that when you tell it how much to transfer, it can either be a number of bits or a number of bytes. In this case, I'm doing typical 8-bit transfers, so it'll be in bytes. And then chip select enable and disable means that when it does the write, it will bring chip select low, and then when it's done, it'll bring chip select high. So usually you want both of those, but if you're doing something special, you could, for example, leave chip select low by getting rid of this. Anyway, so you do the actual write with this function, you give it the handle, you give it a pointer to your array of bytes that'll be transmitted. You tell it how many, in this case bytes, how many bytes it's transferring, which would be 6. It will tell you how many it actually transferred, and you need to tell it the options. And like usual, it'll return FTOK if there's no problem. And so now I'll enter an infinite loop that will read from the gyro and print it out to the command line. So we have an infinite loop, and the first part of it will read from the gyro. Because it's SPI, it's synchronous. You have to transmit 7 bytes, even if you don't really need to. So the first byte tells it we want to read from register 28, and we want bit 6 to be high because that'll be auto increment mode. We want bit 7 to be high, that'll be read mode. We then need to clock in 6 more bits to read from registers 28, 29, 2A, 2B, 2C, and 2D. We will get 7 bytes back, and we'll put them into a array of bytes. Like usual, the API will tell us how many bytes it actually transferred. We need to tell it the options, and in this case we do a read and a write. So that's typically how you do SPI because it is synchronous. Before, when we did a write, that will just ignore the bytes that we got back. But we don't want to ignore them, we want to read now. So read write. And again, you have the handle, you give it a pointer to your receiver buffer, a pointer to your transmit buffer. In this case, we're doing bytes, so how many bytes you want to transfer. It'll tell you how many bytes it transferred, and you give it the options. And again, like usual, you get a status, and if it isn't FTOK, you have a problem. And so now I'm going to interpret the bytes that we got back and extract out the X, Y, and Z velocities. In this block, we interpret the bytes we got back and we print them out. And the way my gyro works is, so we get 7 bytes back. Byte 0, the first byte, will be a dummy byte because it won't be able to read while you're telling it what to read. So byte 1 will be the value for register 28, byte 2 will be the value for register 29, and register 28 is the least significant byte for the x-axis, and register 29 is going to be the most significant byte. And then again for y and z, we have the following registers in the same order. So basically, we read 2 bytes, and they correspond with a 16-bit signed integer for each axis. We print them out, and the plus tells it to always print out the sign, even if it's positive. We want to allocate space for at least 6 characters. It is 16-bit signed, so you can get up to plus and minus 32,000 and change, I believe. And so that's it, basically. So let's go ahead and run it, and hopefully it works. So we have only one channel available. It's channel number 0. I'll type in 0, press enter. It will configure the gyro, and then it will read out the X, Y, and Z velocities. Oh, I forgot to put in the new lines. Okay, so we need a /n right there. Try that again. Use channel number 0. All right. So pick this up. As you can see how it was working just like before. Well, you saw at the beginning. I'm not going to record it again, but you saw how it works, and it works pretty well. So I'm going to go ahead and show the latency timer issue, or not issue, but how it works, which is if we go up to the top, the latency timer part of the channel config structure, if we make that really small, like 1, you'll get much faster reads. So my computer is kind of slow because I have the screen recording software going, and I'm on a 4K monitor, so it's that's kind of why it's all slow. But anyway, so and now you'll see it'll be a lot quicker to read from the SPI device. So it's even, really too fast to read. And if we change that, the maximum value is 255, which will be the slowest you can have it. And so there you see it's very slow. So despite having a 1 megahertz clock and only transferring about 7 bytes for each of these lines, it is incredibly slow. So that's why I used a value of, I believe it was 75, which was a good balance. All right, and there you have it. So yeah, it's a pretty neat little gyro and a neat little FTDI cable. Hope you enjoyed the demo video. If you have any questions, leave them down below. If you have any comments, questions, anything like that. If you like the video, please share it with anybody that you think might benefit from it.